Now we will be continuing with where we have left off in X-rays. Okay, so I told you in the previous lecture that there are two kinds of X-rays. One is continuous X-rays and other is characteristic X-rays. You will have continuous X-rays because of the fact that when some incoming electron hits the target atom, what will happen is a portion of light will be there and some portion will be transferred as kinetic energy. So this emitted light will cause this continuous X-rays. Characteristic X-rays are caused because of the fact that you have electrons revolving around the nucleus. Higher orbit electrons are actually knocked off and we are having this K, L, M, N shells like this. First line of this is K alpha line, second line of this is K beta, third line of this is K gamma like this, and second line in this is L alpha, here it is L beta like this. Now your lambda is Hc by, if you want for K alpha line, you will be writing it as K energy of L minus energy of M, something like this I have explained in the previous lecture. Now in this lecture we will further go deeper into details. Now your characteristic wavelength is because of lack of power previous lecture got interrupted. So now your characteristic X-ray wavelength is what we are going to calculate. So your characteristic wavelength is 1 by lambda is equal to, it is given as R times it is given as R times Z minus B whole square times 1 by N1 square minus 1 by N2 square. Now in some books there is a printing mistake. In some books this R will be missing, it is a printing mistake, it's a printing mistake. So R is there, and your B value is 1 for K alpha X-ray, and if nothing is mentioned take Z is equal to 1. For if nothing is mentioned, always try to take B is equal to 1. Now this is your formula for characteristic wavelength. Now here for different values we are supposed to calculate your wavelength depending upon the need. So let me give you some basic questions and you try to answer those basic questions. So like you have in Bohr's theory, what is that you have? In Bohr's theory, 1 by lambda is equal to Rhz square times 1 by N1 square minus 1 by N2 square like this, right? So in a similar way you will have this, right? So now let us continue further. So let me give some basic questions based on this relation. So the first question is like this. Now let us say the K absorption edge of unknown element is given as 0.171 Armstrong. Identify the element and average wavelengths of K alpha, K beta, K gamma. This is the question given. Now how will you solve to this? I will tell you. Absorption edge means from n equal to infinity to n equal to 1. Absorption edge means from infinity to 1. So according to relation, 1 by lambda is equal to R times Z minus B. If nothing is mentioned, I asked you to consider B is equal to 1 times 1 square minus 1 by N square. So it is actually 1 by N1 square minus 1 by N2 square. If you substitute N2 equal to infinity, this term will become 0, right? So now if that is the case, what will happen? We will have Z minus N1 is 1 if you take from infinity to 1. So you will have z minus 1 whole square is equal to 1 by r lambda. Z minus 1 is under root 1 by r lambda. Z is equal to under root 1 by lambda r plus 1. Now lambda place, your lambda is 0.171 Armstrong, means 10 power minus 10. Rydberg constant R value is 1.097 into 10 power 7 meter inverse. Substitute these two values, that should give you Z value as close to 74. So that is for tungsten. We need to use calculator, but don't worry, in the exam you will get a very good numbers will be perfect. They will give you at least 1 by lambda value is this much, so some up calculation they will try to make it easy. You don't need to worry. Now coming to the second bit, 1 by lambda is r times r times z is 74 minus 1 whole square. For k alpha line you will substitute as 1 by 1 square minus 1 by 2 square. For k beta line it is 1 by lambda is equal to r times your 74 is done. So your next value is 74 minus 1 whole square times 1 by 1 square minus 1 by 3 square. And for k gamma line it is 1 by lambda is equal to r times 74 minus 1 whole square times 1 by 1 square minus 1 by 4 square. You simplify this, whatever you get, that is going to be our final answer. Right. Next, your next question based on this characteristic frequency is, let us say you are given, let us say you are given the wavelength of k alpha line for hydrogen atom is hydrogen like element. It's not hydrogen atom, it is hydrogen like element is 0.32 Armstrongs. Calculate wavelength of k beta line emitted by same element. So pause the video clip, try this question. It hardly takes a minute. So for k alpha line and for k beta line, what is your equation? Let me tell you. So 1 by lambda is equal to r times z minus p whole square times 1 by n1 square minus 1 by n2 square. For k alpha line, 1 by lambda value is 0.32 Armstrong. So 1 by 0.32 Armstrong is equal to r times z minus b whole square times it is it is 1 by n1 square, it is 1 by 1 square minus alpha line, this n2 is 2, so 2 square. For beta line, following the same logic, r times z minus b whole square times 1 by n1 square minus 1 by n2 square. 1 by lambda unknown, some lambda dash is equal to r times z minus b whole square times 1 by 1 square minus 1 by n2 square. That is the second value. If you take the second value for beta line, it is from 3 to 2, so it is 3 square. Divide this equation 1, equation 2, you will get the answer of lambda dash, which is 27 by 32 times 0.32 Armstrongs, which is close to 0.27 Armstrongs. Right. So like this, pretty direct questions will be there and you will be able to solve those. Now next, your next idea is it is Mosleys law. Now in the previous explanation I have given you that okay, I have given you that your characteristic wavelength is r times z minus b whole square times 1 by n1 square minus 1 by n2 square is what I have given. Okay, now this relation is indirectly coming from Bohr's theory. Now, what is this Moseley's law? I will tell you. Okay, what did Moseley do is, okay, he drew a graph. Okay, he drew a graph for what means your characteristic frequency. Okay, this is your characteristic frequency, that is under root of characteristic frequency. Okay, characteristic frequency. Okay, so this is nu. Okay, it is spread as mu, so you can also take it as f, that is up to you. Okay, square root of characteristic frequency. Okay, inside the root you have characteristic frequency and on the axis you have z. Okay, this is your position number of different elements in periodic table. So Moseley, okay, he took the position number of different elements and he plotted a graph, okay, with the characteristic frequency, that is actually indirectly characteristic wavelength, because we know that your velocity is frequency into lambda. So your frequency is kind of, okay, your frequency is v by lambda. So once we know that, okay, it is speed of light c by lambda, because your X-rays they will travel with speed of light. So that become c by lambda means it is cr into z minus b whole square times 1 by n1 square minus 1 by n2 square indirectly. Okay, so here he plotted, okay, he took different wavelengths and plotted two graphs like this and found out that those two graphs are not actually traveling in straight lines like this for different materials. Okay, so this is lambda 1 dash, lambda 1 double dash, this is lambda 1 triple dash, so on. Okay, these are your different wavelengths. Okay, now here what is my point is, okay, here what is my point is, this is for some other element lambda 2 dash, lambda 2 double dash, different wavelengths. Okay, now when he plotted this graph, he observed that there is a straight line like this. Now from this straight line, how did he relate is, okay, you will have an equation in the form of y equal to mx plus c, right? Similarly, your characteristic frequency root v is a times z minus b. This is what he gave, where a and b are constants. Okay, he gave where a and b are constants due to screening, and b is equal to 1 for k alpha X-ray, something like that he gave. Okay, so he told that, okay, okay, so there are some constants, okay, a b are constants. Okay, that much you remember. Okay, don't think too much. Okay, so based on this he gave positions to different elements in the periodic table. Okay, now this relation is very important. Okay, because based on this relation there was a question in the previous mains and NEET. Okay, 2 to 3 times they asked questions on this aspect as well. Okay, now elaborating further this content. Okay, now I am going to prove that this root of nu, that is your characteristic frequency, as a times z minus b from some other relation. Okay, now please concentrate on that part. Okay, so now here, okay, let me do that. Okay, so you have done your Moseley's law basic idea. Okay, it is giving as a times z minus b. Now, okay, proof that your Moseley's law is correct. Okay, just hold on. Now we are going to see the proof from Bohr's model how Moseley's law is valid. Now we have given our characteristic frequency formula as 1 by lambda is equal to r times z minus b whole square times 1 by n1 square minus 1 by n2 square. Now if you look at this r, z minus b whole square, everything, now we know that your velocity is frequency into lambda, c is equal to f into lambda, your f is c by lambda. So multiply with C by lambda is equal to RC times Z minus B whole square times 1 by N1 square minus 1 by N2 square. Okay, your frequency is RC times Z minus B whole square times 1 by N1 square minus 1 by N2 square. Okay, right. So now if you take under root of F, that is equal to Z minus B times under root RC times 1 by N1 square minus 1 by N2 square. Okay, now this term if you correspond it to A, okay, which term? This term if you correspond it to A, not only complete term. Okay, so what is that we are going to get is, okay, this entire term if you assume it to be A, okay, so root of nu we are getting it as A times Z minus B. Okay, so that means your Mosleys law is in accordance with okay, Bohr's model. Okay, right. So based on this there will be some basic questions and you are supposed to do those. Okay, so for example let me give you a question. Okay, this is your Mosleys law. So let me give an application. Your question is this. Okay, K alpha X-rays of aluminium Z is equal to 13 and zinc Z is equal to 30 have wavelengths 887 picometer and 146 picometer respectively. The question is, using Mosleys law, find lambda of K alpha X-ray of iron. Z value is equal to 26. Okay, so try answer to this question. Pause the video clip, try the solution, then I will explain the solution. Come on, give it a try. Now the answer to this question is, okay, for aluminium, okay, basically we know that your root of nu is equal to A times Z minus B. Characteristic frequency value is nu. Now we know that frequency is speed of light by wavelength. So it is under root C by lambda is equal to A times Z minus B. So applying this logic, what will I get is, okay, so under root C by lambda means it is under root 3 into 10 power 8 whole divided by wavelength lambda is 887 into 10 power minus 12, that is equal to A times Z minus B is 13 minus B. This is under root 3 into 10 power 8 by, okay, 146 into 10 power minus 12 is, okay, right, A times 30 minus B. Okay, and this is under root 3 into 10 power 8 by, this is what is that you are supposed to calculate, that will become A times Z minus B. Now this is for iron, this is for okay, zinc, and this is for aluminium. Okay, now from these two equations we are supposed to solve for A and B. Substitute in this and calculate the lambda value. Okay, now how do you solve this is, okay, 10.8.87 is close to 9, so 300s you can assume, and 10 power 8 plus 12 is 10 power 20. 300 means 10 power minus 10. Okay, so your values close to, okay, whatever you are getting, you finish it off. Okay, now it's better if we divide, I suppose, okay, rather than doing this simplification. I think it's better if we divide. Okay, so root C will cancel off, lambda of aluminium, lambda of zinc, if you divide A will cancel off, so you are going to get root of lambda of aluminium by lambda of zinc will be equal to, okay, Z is 30 minus B by 13 minus B, okay. So from here your B value is around 1.4, okay. So divide these two once again, okay, without calculating A, because calculation of A will make it just lengthy. Once again you divide this equation 2 and equation 3, okay. So 30 minus B by 26 minus B is, okay, it is under root lambda by, okay, 146 picometers, this much. Take this B and substitute, simplify, you should get lambda as 198 picometer, okay. So simplification, how you do it is purely your mathematical choice, okay. So you don't need to worry too much about it, okay, right. Next, your next basic idea is, okay, your next basic idea is regarding absorption of X-rays, okay, absorption of X-rays, okay. This comes later in optics, but still, however, for understanding sake, you just take it as information if any basic question comes, okay. So if you have an X-ray that is passing through some medium, let us say this medium's thickness is some X. Now if I naught is the incident intensity, okay, I naught is intensity of incident X-ray and output X-ray is some I, what will happen is your I will be I naught times e power minus mu into x. This is not refractive index, this is absorption coefficient, okay. Mu is not refractive index here, okay, this is absorption coefficient, okay. So this formula you remember, and if any basic questions come, you just please try to apply this basic relation and then try to get the answer, okay. Now next, another important aspect that is required is, okay, basic information is enough, formula and application, okay, that is, okay, X-ray diffraction and which is also nothing but your Bragg's law, okay. So what is this Bragg's law is, okay, the X-rays that you have, okay, X-rays that you have are electromagnetic waves of high energy, electromagnetic waves of high energy with short wavelengths, okay, short wavelengths, okay. Now this may be suitable for diffraction, okay, this makes it suitable for diffraction, okay, this makes it suitable for diffraction, okay. So now because of which what happens, okay, diffraction means bending of light, okay. Now this diffraction is appreciable, okay, or it is considerable, this diffraction is considerable, okay, when the apertures, okay, when the apertures are gap or hole, okay, you can watch my diffraction video, okay. So when the apertures are of, okay, wavelength, when the apertures are of wavelength of order of 1 angstrom, okay, when they are in the order of 1 angstrom, okay, then this diffraction is possible, okay. This 1 angstrom means almost it is close to the size of atom in the crystals, okay. So this diffraction effect, okay, we will consider for different crystals and we will try to develop a relation, okay. Now in case of solid crystals, what will happen is, okay, in case of solid crystals, okay, if one X-ray comes like this and it hits some atom here, it will get reflected, okay. Now in diffraction, okay, you will have this very small wavelength. Now if this diffraction angle is, let us say, some theta here, and if some other ray parallel to this is coming here, okay, what will happen is it gets, okay, diffracted by some other atom in the inner layer. Now if this angle is theta, this angle also will be theta. Now if this interatomic distance is d, now observe carefully. If I drop two perpendiculars, okay, if I drop two perpendiculars here, two perpendiculars here, the path difference that is being traveled is this yellow color part. Okay, the path difference that is actually being traveled is this yellow color part. This angle is 90 minus theta, this is 90, this is theta. This is 90 minus theta, this angle is 90, this is theta. Okay, so the path difference that is extra being traveled is this much. Okay, sorry, I will go to the next page and draw a better diagram. It is better, or else just hold on, I will load a picture. Now I thought it is better, rather than drawing the diagram, explain this. Okay, now if you take a crystal, okay, observe carefully. If this is your interatomic distance or interatomic separation, if this distance is d, which one? Your interatomic separation, I will choose a different color. That interatomic separation is AC is equal to d. Now what will happen is, this angle is 90 degrees. This distance is d. So this distance will become d sin theta on this side. This side also it will become d sin theta. This angle he is assuming it to be theta, because this is 90 minus theta and this is your normal. This angle is 90 minus theta. Okay, now don't think these two are vertically opposite angles. No. Okay, that theta and 90 minus theta are not vertically opposite angles. Okay, so this okay, this diagram must give you clarity for you to not to get confused. Okay, now what will Bragg's law explain is, when diffraction occurs, okay, when diffraction occurs, what will happen is, okay, this path difference that you have compared to the top ray, okay, compared to the top ray, okay, this bottom ray will travel a distance of how much, means 2d sin theta. This 2d sin theta, if it is undergoing interference, okay, what will happen? It will be, okay, if it is, okay, undergoing constructive interference of waves, it will give n lambda. Okay, so this 2d sin theta is equal to n lambda. Okay, this interference is, okay, constructive. Okay, if you consider interference, diffraction, if you are considering, this is the place where minima is occurring, because if you remember previously, d sin theta is equal to path difference delta x. For a single slit diffraction, we are writing d sin theta is equal to n lambda by 2. Even in that diffraction, okay, don't get confused here. Here also it is maxima only, constructive interference. Okay, because we will write d sin theta is equal to n plus half lambda for minima in diffraction. So sorry, for maxima, reverse of interference. Okay, reverse of interference. So here diffraction, you don't talk of interference, you will get confused. So d sin theta is equal to n plus half lambda is for, okay, is the condition for maxima in diffraction. Okay, it will be reverse of YDSC. Okay, if you have learnt wave optics chapter, it will be reverse of YDSC. So that is why your d sin theta is n plus half lambda. So according to that, your d sin theta is n lambda by 2. So here constructive interference will occur. Okay, so strong X-rays, okay, if diffraction happens, okay, strong X-rays will actually be coming out. Okay, and this loss of reflection also will be anyhow obeyed. That you can learn from the detector. Okay, so this equation is only called as your Bragg's law. Okay, now this is your basic information. Okay, and remember, this angle theta is angle with the horizontal, not the vertical. Okay, now what is the advantage? Okay, what is the advantage of Bragg's law? Okay, so Bragg gave this relation, but what is the advantage? What is the final conclusion that you can make? Okay, that is, if X-rays are incident, okay, at some angle theta, okay, they get reflected or observed. They get reflected or observed. Okay. So laws of reflection anyhow they will be obeyed. Angle of incidence will be equal to angle of reflection. Okay. The incident ray, reflected ray, all will be coplanar. Okay. So using this, okay, using this idea, okay, sending monochromatic X-rays, and noting the angles of strong reflection, okay, what is that we can get is interplanar spacing D, and structure can be studied. Okay, structure can be studied. Okay, so that is the advantage of Bragg's law. Okay, so because in the relation 2D sin theta is equal to n lambda, we know that we are sending wavelength. Okay, so this is known to us, this part is known, this theta is known. Okay, obviously this is your unknown. You can get the interatomic spacing distance and all. Okay, so like this you will have some basic questions related to X-rays. Okay, so that basic questions will not be tough at all. You take any reference book and then you learn everything. Okay, now what is the summary? Okay, so first lecture it took around 30 minutes, this took 33 minutes. So within 1 hour we have finished X-rays, and any question you will be able to solve it. Okay, so before that I forgot, I did not give properties of X-rays. Sorry. So the properties of X-rays that you have are not much, basic definitions only. Okay, so what are the properties means? Okay, so they travel with, so electromagnetic waves, they travel with speed c equal to 3 into 10 power 8 meters per second. They are neutral, so not affected by electric or magnetic field. Okay, they do not cause magnetic moment, mu bar or m bar, whatever symbol you take. Magnetic moment is na bar. Okay, because they don't have any charge, nothing will happen. Okay, next, they can ionize gases, cause fluorescence. Fluorescence means ability to emit light. Okay, even after the radiation is removed. Okay, right, then they have destructive effect on living tissues. Okay, but morely X-ray radiation is good only. Okay, because we can identify the fractures and all. Okay, so these properties are enough, and then followed by, okay, your summary. What is the summary that we have seen? So your summary is, okay, so your graph that you have will have minimum this thing, then you have k alpha line here, k beta line here. So for continuous X-rays, okay, your lambda min is hc by e times v. This v is called accelerating potential. Next, for characteristic X-rays, this graph you should remember. So this is your k alpha, k beta, k gamma, then followed by L alpha, L beta, like this. Your characteristic wavelength is 1 by lambda equal to r times z minus b whole square times 1 by n1 square minus 1 by n2 square, and from this graph you should be able to substitute the values. Okay, this is for characteristic X-rays. Okay, continuous X-rays mostly theoretical questions, you can tick the answer directly if at all if question comes. Then followed by your Mosleys law is root of nu is equal to a times z minus b, where a comma b are constants. Here B value is equal to 1 for K alpha X-ray. Okay, then your absorption I is equal to I naught times e power minus mu x, where mu is your absorption coefficient, I naught is incident intensity. Okay, then followed by you have your Bragg's law, which is 2d sin theta is equal to n lambda. Here I told you to remember that theta is angle with horizontal. Okay, and d is the distance, interatomic distance between the layers, interatomic distance between layers, and usually it is in the order of Armstrongs. Okay, so this is what I have given. Okay, right. So with this your X-rays is done from my side. Okay, from your side what is it you are supposed to do is, okay, take any book, start randomly solving the questions and do as many as you can. Okay, I will upload problem solving sessions for each and every chapter soon. Okay, so that's all for today. Thank you. End of X-rays. Okay, 1 hour is enough, so please don't skip this topic in the exam.